brought to you by FLOWSPARK Media.
This opens up so many more avenues of creativity for how we design a robot, how we create energy. Oftentimes our limitation is really the materials that we have at hand. This is actually, I think, where we are progressing the furthest and where we also see a lot of biomimicry.
Hey guys, Eric here, and welcome back to another episode of the Science-Centric Podcast. This is a show where we have thought-provoking conversations about science, society, and the natural world. And who am I? I'm a filmmaker and journalist with a passion for science and nature, and I also happen to be the host of this show. Now, before we dive into this episode, just a quick reminder to subscribe to the channel and hit that little bell for notifications when new content goes live. Thanks for helping this little channel to grow and for making the world a little more science-centric. So if you didn't already know, this episode is all about biomimicry. If you've ever used Velcro, taken an aspirin, or bought IKEA furniture, you've used a biomimetic product, meaning it imitates the structure or function of something already found in nature. Our guest in this episode, Kristy Hamilton, knows this topic well. She's a journalist and author who has written a whole book, Nature's Wildest Ideas, about the latest and greatest biomimetic inventions. Now, I'll just preface this episode with the fact that I was recovering from COVID when we recorded, so I'm a little bit unfocused. Fortunately, Kristy was very clear and articulate and kept things on track. So thank you to Kristy. And without further ado, Kristy, thanks for joining us and thanks for being here.
Yeah, thank you for having me.
Cool. So what is biomimicry?
Yeah, so you can find a few definitions online for what biomimicry is, but how I define biomimicry is that biomimicry is a practice that learns from and mimics the strategies found in nature to help us humans solve design challenges. So how can we look to nature to solve some of the problems that we're facing with clean energy or with pollution or with even structural design? How can we look towards how evolution has done it over billions of years to design our way towards something that is either more efficient, more sustainable, or, helps us with our health?
So what advantages do biological systems have in terms of design versus something that we would design in more of a, top-down way?
That's actually a really good question. So animals often develop very niche strategies for the environment that they're in. So they're not good at everything. They're usually very good at one specific thing. So we're not looking to one animal to help us solve all our ails, right? We're actually saying, wow, this creature is so good at this one thing. And can we take inspiration from that? Can we use that and incorporate it into our own designs? Because sometimes we don't have access maybe to the same materials that animals are using, right? Or we can't harness the energy of the sun quite as well as animals can yet. But we can be inspired by this really efficient design process that they've developed, because energy is the key resource in the animal kingdom, right? They don't want to have to overproduce something to get a benefit. If they need to get food, they want to do it in the most efficient way possible. And oftentimes that means they design in a very smart fashion, although of course evolution has no foresight in mind, but it ends up being a very smart solution to a design challenge.
And I guess animals, biological systems, creatures, not just animals, plants obviously too, but they have the advantage of time, right? They've had bazillions of years to figure this stuff out, or their genes have had bazillions of years to figure this stuff out, whereas we're trying to do this in a year or 2 years or 10 years.
Exactly. It's a benefit for them, and it's also can be a pitfall in our design. in the sense that they've had all these billions of years to design something so perfectly concocted for their environment, right? But then how do we humans do the same thing? So, like coral, for example, they take a very slow time to build their skeletons. And yet we've taken inspiration from coral to help us create concrete that builds our buildings, right? To make a greener cement with less carbon dioxide. But they do it so slowly, and we need to process and build things really quickly. So sometimes what we do is we like supercharge nature in science. We say, wow, this is amazing. How can we speed it up? Mm-hmm. So time works to their advantage in terms of the long evolutionary time and the brilliant ideas that has come from that, has sprung from those billions of years. But then at the same time, maybe a species can't pivot, like a single species in this moment can't pivot quite as quickly as we could with our science.
Mm-hmm. Yeah, I mean, I think of... in particular with like plant evolution and pharmaceuticals, I think that's one that, I mean, is comes foremost to my mind in terms of, long processes of evolution, and then we're mimicking these processes to create new drugs, right? Is that a kind of avenue of biomimicry that you've explored?
It's a huge one. Yeah, I have a chapter dedicated to health. It's actually I focus on a reptile, but a lot of the examples towards the end of that chapter is plants, because so much of our medicine is inspired by plants in the natural world. They just have this great chemical diversity. It's really the diversity of the plant kingdom that is so extraordinary and that has really worked well to our advantage. Same with venoms. Oddly enough, it's very much plants and venoms that I think it can sound woo-woo to people because they're like, oh, herbal remedies, you must be talking about some kind of witchcraft. But it's not at all. Like our breast cancer medications, our penicillin, our, a whole bunch of these like really important medications that affect millions of people have been inspired by plants and animals and their venoms. And it's pretty incredible stuff. And I'm surprised that we tend to like distance that association, Yeah,
I think when people think about that, they don't think of that's biomimicry. They're thinking of something that's more in the realm of like engineering, in particular, structural,
and it is
or something
a bit.
Like that.
Yeah, that's actually what is so interesting about biomimicry is that it's an interdisciplinary field. So if you look at, MIT or Harvard, they have sole departments dedicated to biomimetic science, but they're bringing in people who are chemists, who are engineers, who are designers, and they're getting them to all sort of sit at the table and say, hey, we have this problem. How can we solve it? And so it really is kind of getting all of those people together, like you say, right? And be like, this is a challenge. What can we do? I'm going to bring my expertise from this angle, from this angle, from this angle. And yeah.
That's really interesting. Yeah. So if you were going to go into the field of like biomimetics, I guess it would be, that's a very much an interdisciplinary field, right? I mean, are the scientists that you encountered, are they specialists, or are they more interdisciplinary, or do they work on teams? I mean, I guess, or maybe there's a combination.
It's a good question. I have often found that they're very much specialists with a very creative mind. They often lead teams in these really forward-thinking ideas, and they're really good at gathering partners who can help them, enact their ideas, experiment with their ideas in the lab. But I wouldn't say there's anyone who is a biomimetic specialist. I think you can get a 2-year degree program, but I would very much say they're more communicators than they are scientists, because usually nature is so freaking intricate, it's so intricate. We still struggle to even understand how to do it. I mean, most of the things that we build with are steel and solid and right angles, and nature is flexible and flesh, and very few right angles in the animal kingdom. And so we still struggle to even understand how to do that. So oftentimes they have to be specialists at the table. So somebody who's a specialist in materials, someone who's a specialist in energy, and then how can they synthesize that specialty into something that is biomimicry.
Yeah, it's kind of amazing when you think about the fact that we need all of those specialists at the table to do something that's maybe happening in one cell of a body, of an organism, that's
it's humbling.
That's kind of wild. Like,
It's humbling. I have found myself very humbled throughout this process. I'm incredibly astonished by what scientists can do. And I'm also incredibly humbled by how far we are from what a simple insect can do,
Yeah, I remember seeing a diagram or something that someone had created that was it was like creating a factory that would do a biological process that happens, on a micro scale inside of an organism. And it's like this huge factory with all these, vats and pistons and, things, steam pumps and all this stuff.
Yeah, you know what that reminds me of? It reminds me of this line that I have, which is that it's so much easier to make things bigger. In terms of like what we can do as humans, it's so much easier for us to make big things. As you see with our computers, right? They slowly get smaller because it's actually harder to make things smaller than it is to make things bigger. And yet life on this planet started small. And then got bigger and then maybe got smaller again, depending on how evolution worked. But it started small, and we often like to start big and then move small.
Hey there. If you made it this far through the episode, you're probably enjoying this conversation and learning a few new things along the way. If so, I'd really appreciate your support so that we can bring you even more quality science and nature content to YouTube. Head on over to our Patreon page to find out how you can support us directly. We have 3 tiers you can join, and they start at only $1 a month. The link's in the description below. And thank you to our existing patrons for their support. Now on with the show. Maybe we could segue a little bit to talking about some of these technologies that you talk about in the book. So let's start with what's your favorite one that you came across that surprised you?
Yes. My favorite one is how a lobster inspired an X-ray telescope that is now on a satellite heading towards Mercury, because it's mind-blowing to me that something in space was inspired by something that lives deep in dark waters, and how we got there. And also because why does nobody else really seem to talk about this, or why does no one else know that much about it? There's actually a fair amount of material out there. I also did interviews, but we seem to focus on things like gecko tape and, kind of the simple inventions. And yet there are so many that have won a Nobel Prize or were launched into outer space or just had massive impact. And so the lobster-inspired telescope, as NASA calls it, it's, very literal to its name, which is why I'm also surprised it didn't get more media liftoff, is my favorite, because it really showcases, again, like a shift of view, right? So we understand how we view the world, but it wasn't until we explored how another creature views the world, how they use a different biological design for the eye to design a telescope that had eluded us for decades. It was something that astronomers were working on for decades, because an X-ray is something like 100 to 1,000 times more powerful than an optical photon. So what we can see with our senses, right? And so it just passes right through telescopes, just passes right through our technology. It's too powerful in many ways to catch. So they ended up looking to a lobster, of all things, to create this sort of dreamed of telescope that took many decades after even the initial vision to develop, because the technology was so sophisticated. And you think about that, like a technology so sophisticated, and it's that beady little eye in a lobster, right? Like that's just so crazy to me. And so how that happened, Do you want to know?
Yeah, sure.
Okay. So what is so special about lobster eyes? And what's so special is that they actually use millions of tiny mirrored tubes in their eyes. We have this sort of like jelly, this goo that we use, and we use refraction, etc. We flip things upside down. They don't. They see the world exactly as it is, but through these millions of mirrors. And people never even thought to consider that, because how can you have mirrors in nature? It's a human invention, you would think, but it's not. You can see iridescence on a butterfly wing. You can see iridescence in quite a few places. And nature has used essentially what is guanine and cytoplasm, I believe, to create this natural world mirror. And they can do it at 20 microns, which is 20 times smaller than the period at the end of a sentence. And a lobster's eye, that black, beady little eye, has millions of tiny microchannels that are mirrored, and it bounces light off of two sides and then enters its neural ganglia. It goes into its brain. It can kind of get a visual picture of the world in these really dark, murky places that it has to explore to find food.
So is the idea that this mirrored tube is amplifying that light in maybe the same way like a fiber optic cable would?
Not quite. It's actually what it's helping to do is it's almost taking some of the energy off, so to speak. So what it's doing is, since it's hitting two sides, it's being focused onto a single point, but it's not just coming straight on. It's being skimmed off at an angle. And by doing this, it's actually building a picture that we can see, but it's not at the full straight on strength that like an X-ray photon would just beam right through the telescope. So it's kind of this weird optical trickery to let it skim off the edge a bit and bounce twice before it enters that focal lens. So it's capturing X-rays, and this is for astronomers, right? We actually use a similar technology now to, peer underwater at fish in nets to see the health of fish and stuff. So they use NASA's technologies and ESA's technology for other purposes. But here they're trying to capture X-rays, and X-rays and gamma rays are emitted by massive explosions in the universe, some of the most powerful explosions in the universe. And these most powerful explosions in the universe are also where some of our most fundamental elements are formed. It's where it's spread throughout the universe, and they start to collide and, become essentially many, many millions of years down the line, many billions of years down the line, it becomes what you and I are. It's these big explosions that have sort of garnered that saying that we are the stuff of stardust, right?
Yes,
We come
Carl
from
Sagan,
stardust. Yeah. It's these big explosions that we want to understand, to better understand the universe and ourselves and our origins. But it was always too powerful for us to capture. We can do visible light, like with Hubble, but how do you capture X-rays? And it was the lobster that held the answer.
That's so cool.
Yeah.
So the idea is that we want to, we're going backwards. We want to get a picture of what's happening in the universe, and we want to capture these X-rays. But couldn't we just sort of turn down the volume on the image, to capture those X-rays? It's not possible to kind of, to just, come up with a less sensitive detection method? Or is that essentially what this is? Is that it's
essentially what it is, but you still want a clear picture. And so that's kind of the weird struggle that the push-pull that they have to deal with, because it's not that it's less sensitive because it will beam right. It's just that it's so powerful. It's how do you capture something that is just so powerful?
Gotcha.
And
so you're talking actually about cosmic rays.
Cosmic rays.
Yes. Okay. Sorry, I wasn't making that connection.
Oh, not we use X-rays for medical scanning devices and stuff.
Yeah.
But this is the X-rays from the universe.
These are high energy cosmic rays that are coming in.
Exactly. Like,
Yeah.
have you ever seen like NASA images, right, of stars and nebula and stuff? And they often color the images in these different colors. And they're trying to sort of showcase to you different wavelengths that we can't see. So there's visible, but then they're also trying to do the gamma rays or the X-rays or the, UV often. They're trying to like sort of showcase what we cannot see. We're trying to use all the tools we can to capture the world that is invisible to us, which is a lot of it.
Cool. Let's talk about tardigrades, because I think everybody loves water bears. And
They do.
How are they helping us with healthcare?
Yes.
And what are tardigrades?
It's a good question. Tardigrades are these either very ugly or very cute creatures, depending on if you're someone who tends to find the ugly slightly cute. They are these very, very tiny, tiny, tiny creatures. You usually have to use a microscope to see them. There are thousands of species of tardigrades. We tend to just kind of clump them into that category, tardigrades. And they have 6 legs with little claws on them, and they kind of just mosey along eating things like moss and algae. And you often find them in ponds or, essentially areas that are mildly wet. You can also find them in very wet places as well. But the ones that scientists focus on tend to be places that are like a pond that can dry up really quickly. Like a small area, a small water source, essentially, that can dry up really quickly, but can then also refill back with water again very quickly. And that...
And I was going to ask, they look like little... are they animals? Would they be considered animals?
They are animals, yes, yeah.
But they look somewhat complex, but I think they're actually really simple, right? They're not composed of that many cells.
No, I think they're just... I don't even know exactly how many cells they're composed of, but they're very simple creatures. They don't, it's when they eat things, the nutrients, right, just touches all their cells and provides what they need. They don't have a gastrointestinal tract that, has to digest all the foods and stuff. It's like a very, very simple creature with like a very incredible superpower. And then what are some of the amazing things that tardigrades can do? Yeah. And why? How does that relate to medicine? Yeah, it's a good question. And so these tardigrades have had to develop a way to essentially be dried out, right? They live in these ponds, these like very ephemeral landscapes. And so if we were to dry out all of our cellular bits, all the little like bits and pieces, like proteins and stuff inside our bodies would just rub together and, break apart. They would break their shape and we would essentially die, which is why we can't last more than 3-4 days really without water. But tardigrades can last for 30 plus years. And so there has to be something that they're doing inside their bodies that is helping them preserve themselves. And so scientists wanted to look towards this because our medicines, it's very hard to transport our medicines without keeping it on ice or keeping it really cold. Our vaccines in particular, they're very, very temperature sensitive. And so is there a way that we can kind of do what the tardigrade is doing and preserve these medicines, right, until they reach their desired location? And so that's what the scientists were doing. And they did find that these tardigrades created something pretty impressive, which is trehalose. And trehalose kind of just, it's doing its thing. It's when it's in its spot, when the tardigrade is happy and in water, it's doing its thing, like nothing's really happening. But the moment the tardigrade dries up or desiccates, as scientists call it, it freezes into this internal cast. So almost like becomes glass, and it just keeps everything in its place. So that if you had to make the equivalent with us, right, our hearts wouldn't collapse onto our liver or anything. It would keep everything separated from each other. And then once water comes back, that trehalose melts, kind of like a sugar cube in a teacup. And it kind of just goes back to doing its thing, but it can essentially let that creature revitalize itself. And so we used a similar technique to try to keep all the little bits and pieces of medicine, stored and structured while we're transporting them to their specific location.
And so are we actually using this trehalose molecule to do that? Or is it something different?
Well, I think they've synthesized trehalose, so they don't have to get it from the tardigrades themselves. We've actually been able to sort of duplicate it, but it is still trehalose. They often put it with other chemicals, depending on the structure of the medicine itself. But we use it for many different kinds of cancer medications, vaccines. It can help preserve experiments or proteins that scientists want to look at in the lab, so they don't have to depend so heavily on the cold chain, which we've lived so many years without refrigeration, and then in this century we just depend so much on keeping things cool and very temperature cool. Like, there's no extremes, no swings in temperature, and our labs cost hundreds and thousands of dollars. And if the lights go out and we lose electricity, oftentimes we lose our experiments too. So scientists are looking for ways that we can have a backup, a way to, not have quite a catastrophic collapse of these labs, but also of our medications.
And this trehalose product has like a brand name, right? It's actually something that someone patented, if I recall.
I believe it was patented for a while. I think the patent may have expired by now.
Oh, okay.
But it's used in all sorts of things. It's even used in our cosmetics, so I don't think it's brand patented anymore.
Cool.
That would be my best guess.
Do you enjoy books about science and nature as much as I do? They bring a lot of information together and help you learn about science and the natural world on a much deeper level than you just get from consuming news. Well, we've curated a great list of books over at our website on a page we call the Reading Room. It also features the books of all the authors that we've had on this podcast. Any purchases made through the Reading Room help support our channel with no added cost to you. Check it out at sciencecentric.com or look for a link in the description below. So let's talk about the Gila monster. So how is the Gila monster? First of all, let's just clarify, what is the Gila monster? And then how is the Gila monster helping to fight type 2 diabetes? Not
type 2
1,
diabetes,
type 2, right?
Yeah.
Yeah.
Mm-hmm. So a Gila monster is a 2-foot lizard with black and orange pebbly skin that lives in the deserts of Arizona, essentially the southeastern United States. And it is a very scary looking creature that is very shy. It is all looks and very little scare factor if you actually research the lizard. It does have a painful bite that makes it seem like it's venomous, but it is not toxic really to us. We will not die from a Gila monster bite. But that venom, their spit is kind of composed of this venom that just creates a painful bite. It makes the creatures run away that try to eat it. And then there's also the saliva part of their spit. And it's that saliva that scientists find so interesting. And why they even looked at these, 2-foot lizards is because they do this thing where they like to gorge on food, if possible. So they'll gorge on eggs, say, and then they'll go for 3 months without food. And then they'll gorge again, and they spike their sugar levels inside their bodies like 30 times. Like, there's a massive spike of sugar in their bodies. And if that would happen to us, we would certainly have a disease. Like, our body is not in stasis. It's not doing well. Like, it's freaking out, right? But these lizards just mosey along. They go back to their burrow, and they're happy as can be. And a scientist, a doctor called Dr. John Eng, he noticed that when a Gila monster bit, say like a baby rabbit, not nice visual, but that's what they eat. And he noticed that their pancreas, the rabbit's pancreas, would swell, would engorge. And he was like, okay, well, that's where insulin is produced. So they must be doing something to this organ in the body that releases insulin. And so he looked more into that, and he realized that there is sort of this, it's a bit difficult to describe, but essentially that saliva that helps them digest and moderate those huge spikes in sugar, it does also engorge the pancreas of these creatures because it releases a ton of insulin in their bodies. And type 2 diabetics have either a difficulty releasing insulin, they don't release enough insulin, or they're insulin resistant. And so they need more insulin. Essentially, one of our ways to combat type 2 diabetes is just to give them more insulin. Because even if they do make enough insulin, they're resistant, so we just dose them higher. And then some type 2 diabetics just don't make enough insulin themselves. And so we try to supplement what they don't make. And they looked to this Gila monster to create a better type 2 diabetes medication, because diabetes medications often come with unwanted side effects. So pharmaceutical companies are still looking for a better, almost kind of softer version for these diabetic patients. And oftentimes there's unwanted weight gain, which doesn't necessarily help a type 2 diabetic that is trying to lose weight. And they found that this molecule called exendin 4, but the medication's name is Byetta, or, fans of Byetta who first heard about the correlation call the medication Lizzie after the lizard. They appreciated the side effects in the sense that they actually lost on average something like 5 pounds. So there's no real significant weight loss factor here. It's not a weight loss pill, but they didn't gain weight, right? And so oftentimes we use Byetta to supplement other stronger medications. So we use 2 medications at the same time. It's a very complicated. Hormones in the body are so complicated. And so if we use Byetta currently for millions of type 2 diabetic patients.
Yeah. I mean, that's so interesting that the way that medication, that compound you mentioned, what's it called? Zen 4?
It's called exendin 4.
Exendin 4.
It's
so interesting the way that was discovered. The doctor who discovered this, did he come across it just because of this phenomena of the baby rabbit's pancreas being engorged? Was that like the main way that was discovered?
Yeah. His origin story is maybe a little bit less fascinating, but very stereotypically a scientist. So he was reading papers about the effects of what a Gila monster does to the pancreas of these rabbits. And so then he ordered some for himself. What's kind of fascinating about his story is that he came up with this really incredible discovery, and he patented it, and he could get no one to buy into it. And so he held on this patent for years and years and years. He went to a conference by himself with a lanyard. He's representing himself, essentially. There's no company behind him. And someone happened upon his poster presentation, essentially, in the corner of this conference, and was like, okay, this is amazing. We want to hear more about this discovery. This is something that we're looking for as well. And so then he finally, teamed up with eventually 2 major companies and pharmaceutical companies. But it remained undiscovered besides him, for quite some time.
And what was the time frame there? I mean, was it because I feel like people take this a little more seriously now in terms of drug discovery. Did this happen a while back in terms of?
This did happen a while back. This was decades ago. It is an interesting question as to why it didn't get picked up. he certainly was trying to have it get picked up. He was doing research. He was in a lab of a Nobel Prize winning scientist. So technically he had all the reasons for it to be seen and picked up. But as happens in science, it's often swamped with lots of information. And so these discoveries can be very slow to fruition. It's also it's much more difficult, I think, in medicine than in plain inventions or something, in the sense that there's so many regulatory hurdles that medications have to go through that people are very hesitant to take anything new on, especially if something sounds like it came from this weird 2-foot lizard,
Yeah.
So it's a tough sell, and yet it's also somehow an easy sell, right? Like, it sounds so cool for the media and stuff, but maybe for hesitant pharmaceutical companies, it's like, well, like, what's going on here,
Yeah. I mean, I just kind of find it surprising in a way, because I was thinking about Taxol, which was discovered in yew trees. Mm-hmm. Have you ever looked into that story, by the way? That's a really interesting, crazy story, how they found that. Oh yeah. I wrote something about that a long time ago, but it was they kind of just took this swath of forest, ground everything up, and just looked for any compound that they could find that might have some pharmaceutical activity.
Oh, wow.
And then found this Taxol compound. And that was the only one out of this massive effort.
Oh, wow. Okay. Yeah. I hear they're doing something similar these days, although I think they're trying to do it a little bit more gently than just taking a bunch of nature and grinding it up. But they're doing something similar with sponges that live in the sea.
Yeah. Mm-hmm. And then the other one I thought of was, I find this stuff fascinating, was the ivermectin thing. Have you ever looked into that story at all?
No.
Like, I know it's been in the news as kind of like, don't take ivermectin because it's not going to help your COVID. But that's another one where it came from this golf course in Japan. It was some soil sample, and they never found this bacteria again that made this compound.
Oh, I love that story. Okay, yeah, I'm definitely researching that story after this.
It's crazy. It's crazy.
I love that.
Just so random. And, they've never found it again. And then it went on to win, it is a Nobel Prize winning medicine, but it was, just not I mean, people were not insane for thinking it might help with COVID. It just didn't end up helping very much. So,
right. Yeah. From a golf course.
Yeah.
Like, what?
I mean, it can treat a lot of stuff. That's the interesting thing about it. So what do corals have to teach us about making better cement?
Yeah, it's a good question. So then you have to think, the next question is, what is so bad about cement, right? Or concrete? Cement is kind of like the flour that goes into concrete, which is like the final finished product, a cake, so to speak. If you want to, what's the difference between concrete and cement? And so concrete is responsible for 8% of the world's carbon dioxide emissions. So apart from the US and China, it is its own third country, essentially, in terms of emissions. And so we are looking for ways that we can minimize these emissions. And it's really only come to the forefront of our attention in the last 5 to 10 years. Recently, Bill Gates has also sort of taken this initiative to work with concrete factories and industry. And so it's ripe for change. And we are still building at massive speed. So the UN has the statistic that says that we are going to double our buildings, by the time that our children's babies are our age. So there will be double the buildings on this planet. And we probably don't want to go about it doing the same thing that we've always done, considering we're in a climate change crisis, We're at a time to pivot. So we have some companies who are looking at coral and how they create their skeletons to develop a 98% less polluting, less, it essentially has 99% less carbon emissions than traditional concrete.
Mm-hmm. And why is that? Why does it?
Yeah,
I think that gets back to maybe what we were talking about initially, which was, lack of waste in the process, right? I mean, if you're releasing a bunch of waste not, want not, if you're releasing a bunch of, is it CO2 that it gets released in the process of making concrete?
It is. It's CO2. And to your question, why? There's a whole bunch of reasons with like the mining, of course, and the transportation, but really it's because they have to fire up the limestone, which they want to get calcium essentially from the limestone. They have to fire up these huge kilns to thousands of degrees Celsius. And it's just hugely carbon intensive. It's a process that just takes it's almost a 1-to-1 ratio. So like 1 ton of cement emits, is equivalent to 1 ton of carbon that goes into our atmosphere.
Okay. Gotcha. So it's the heating process that's
process. Yeah. And so they've developed a way to do it without heating these bricks.
And this comes from corals?
It comes from coral. Yeah. And how they create their skeletons.
How does that work?
It works. Yeah. Well, oftentimes people forget that hard coral in the ocean is an animal just like you and I. And so when they exhale, they release carbon dioxide. And that carbon dioxide reacts with calcium in the water and it creates those skeletons that you see. So they push ever so slightly away from a surface that they're on. And then they use these chemicals. They use this reaction essentially with their breath and the ocean's calcium to fill in their architecture, fill in that skeleton. And a company is using something similar, not coral because it's too slow. They grow like a few centimeters a year, which is way too slow for us, right? But they love this idea that it's creating what we're essentially trying to get from our limestone, right? We're trying to get all that calcium from our limestone. I mean, yet you have a creature who's kind of creating that structure that we want to create as well. And so what they do is they get aggregate sand, recycled aggregate sand, which we have tons of. You demolish buildings too. And so they use this aggregate sand and then they put nutrients, they sprinkle nutrients essentially on these bricks, and there's bacteria in these sand bricks. They're not hardened yet. There's bacteria, and these bacteria do something very similar as well. They create that calcium carbonate essentially between the grains of sand, and they like stick all those grains of the sand together. They essentially are the glue that holds it together and makes it really strong. And experiments have shown that it can really hold up to some impressive testing. They use them at, I think, drop boxes, offices currently. They're being used at airports. It's being slow in some ways and fast to take up because people are hesitant to use a new material in case anything goes wrong. So they're doing their due diligence and they're taking it slowly, but it's a big company and it has big promise.
Is that something that can be done on scale in the same way that creating concrete can?
It's a great question.
Because the, bacteria, their output, at least individually, is quite small.
It is, but bacteria, you can just create billions and billions of bacteria so easily, right? And so you do need warehouse space, but it only takes 3 to 5 days to create these concrete bricks. So it's actually exceptionally quick compared to our current traditional standard concrete industry. Now, where things can get a little tricky, you may say, is that our concrete is not just concrete. We have concrete with like steel bars put into them. We start to do much more complex things with concrete, but Biomason, as the company is called, is also starting to show that they too can do creative things with these bricks. They even have one that I think is just fun, right? And it would be perfect to use in Seattle, where you can have what looks like just a concrete walk, right? But when rain hits it, it actually can showcase a slightly darker, pattern or image on the ground. And so they can make glow in the dark sidewalks. Bacteria are incredible, and we often don't harness them enough. And it's a beautiful use of biomimicry and also kind of scientific innovation.
Yeah, it seems like you could also, throw some sand and bacteria in some oddly shaped space and fill it up, if you gave it time.
That's actually a really interesting point. Yeah, I wonder if they could make it more mobile to the location, right? Like it didn't have to just be warehouses, although that's useful too, but could they actually create more of a device and just use that device on site? That would be pretty cool.
Yeah. Yeah, you could just, have a hose and make a building out of it. It's like a big...
You're concrete 3D gardeners. Yeah.
Yeah, big 3D printer kind of with a garden hose or something like that. Do you work for a science or technology-focused organization and would like to create video content but don't know where to start? Well, my company, FLOWSPARK Media, the publisher of this podcast, can help you. We are a one-stop shop that can provide content strategy, video production, and even social media management. Our previous clients include educational institutions, academic publishers, trade organizations, and aerospace companies. These are innovative, world-changing organizations who are leading humanity toward a brighter future. Learn more at flowspark.com or look for the link in the description below. So let's talk about why, or how spiders, let's say, are helping birds not to crash into windows. And it's not intentionally.
It may not be intentionally, yes.
They don't care if birds hit windows. They probably want to eat the birds. So
yes, yeah. That is such an interesting origin story because initially there was research to suggest that that spider webs reflect UV, and it could be to prevent birds from crashing into their spider webs. We now know that it could also be to attract insects to the spider web. There could be a whole host of reasons, and people are skeptical. It's because to deter birds essentially from crashing into their webs, although that might be a reason too. It could be multiple reasons, right? But a company looked into this. They loved this research. They looked into it and they knew that we have this design issue with our windows where 100 to 1 billion birds each year die by window collisions in the United States alone, right? A massive amount of birds die by window collisions. And is there a way that we can preserve our bird population and the diversity of our bird population by using maybe a unique system found in nature? So here they looked to the spider webs and how they use UV. This would be a great solution because humans can't see UV, right? So our windows would remain clear, we can see through them, but birds could see them and they would be like, nope, don't want to go there. I'm going to go around the building instead of smack into it, right? And so they've been doing, and they still continue to do, tons of testing for this. They have, wood tunnels set up with different kinds of glass at the end, and they have birds fly at it, and then they release them. There's a net in front, by the way, so they don't, have the birds crash into the windows, and then they're like, okay, you're done. No, they have a net. They catch them. It's all humane. They let them go free, but they record how many times they crash onto which side of this tunnel. And they did find that UV inscribed windows, essentially what they kind of refer to as like avian hieroglyphics, things that only the birds can see. They do work to a degree. 80 of the 100 birds, say, did avoid, the UV window, and 20 were like, hey, I don't see it, and they just crashed right into that side. But we also have better alternatives out there. So it's better than a traditional glass window. It's not the best option that we have.
I just wanted to interject and just ask you what are avian hieroglyphics?
Yeah, I love this terminology that they use. So avian hieroglyphics, right? It's like something that only the birds can understand and see, but that we cannot comprehend or see in our windows, but it's there. So it's something that they can read or see out there, but the humans cannot see. And so they kind of have this coined term that it's avian hieroglyphics, right? Which is a fun way of describing it. it's also not necessarily the complete story. So I think you'll find online that we've somehow stopped bird collisions with these UV windows, and yet that's not entirely the full story. And they're also very expensive, these windows. It's hard to embed UV into windows. And oftentimes windows are still convoluted by reflections from bushes or from light on the inside of a building and it's dark outside, right? And it makes it harder to see that UV in the windows themselves.
So are the other approaches that people are looking at to stopping these bird collisions, are those also based on biomimicry, or are they just using more traditional methods that they invented?
No, they're just using common sense. And I love this one so much. They essentially, the best methods are parachute cords, which are like strings, 4 inches apart on windows that kind of wave back and forth, or chart tape. You may have seen dots. Essentially, stickers are the best way to prevent bird collisions. But oftentimes as humans, right, we want to have a clear view out our windows. And so it's almost this moral dilemma, right? Like, do we want to prevent bird deaths or do we want to see out our windows clearly? That's kind of the question on the table right now, because that's what we're struggling with. We don't have a perfect answer yet, unless you think maybe chart tape, like really cheap chart tape or parachute cords is the answer here.
I love that it's like a simple solution. It's like, just put some duct tape on the window and,
yep,
and
exactly.
That's the best solution.
And yet it's like a really intense moral dilemma. People actually have discussions about this, right? Like, well, we can't disrupt the view. You can still see outside, by the way. It's just like not as perfectly, right? But there's like literally discussions that people have about this. Like, can we put tape on windows? Can we not put tape on windows? What will people think about that? It's just amazing. It's human psychology.
Anything to preserve that view, I guess.
Mm-hmm.
My question is, do you think that we're going to see more of this biomimicry thing, this biomimicry technology in the future? And do you think that it's important to humanity's future?
Yeah, I do think we will see more biomimicry in the future. I think where we are going to advance the quickest is in material science. And so it doesn't sound sexy, but it is. It goes back to what I was saying at the beginning, which is we construct everything with steel and harsh corners, right? But we now have nanotechnology and really interesting material engineering where we're now trying to make flexible surfaces and electronics that can lay flat on these flexible surfaces. And maybe a battery doesn't have to be just a battery. Maybe a battery can act kind of like our body fat and be all across the device, right? Or all across the robot. And it doesn't just have to carry a huge battery at its core. And this opens up so many more avenues of creativity for how we design a robot, how we create energy, how we really use our science, because oftentimes our limitation is really the materials that we have at hand. But this is actually, I think, where we are progressing the furthest and where we also see a lot of biomimicry.
Interesting.
Yeah.
Yeah, material science is, like you said, not the sexiest topic. It seems a little dry, but then you see those papers come out and it's like, oh my God, this, tube is moving like a snake, or, they've invented this new rubber that can, flex and bend in origami shapes. And you're like, oh my God, that's amazing. So
exactly. Because if you think about it, we have like DNA, right? That can just pack into a super small space. And yet if you really were to just take it out, it's so long, right? Well, is there a way that we can also pack things into tighter spaces? Is there a way that we can, get inside places we have never got inside of, including our own bodies, right? Yeah, material science is just so ripe for so many innovations, and it's really exciting.
Cool. So where can people find this book? And where can they find you online?
Online. Okay. Just where can they find me? Not going to give away my home address.
Not in a coffee shop somewhere.
Yeah. So they can pretty much find the book anywhere online on all major platforms like Amazon and Barnes and Noble. There's also indie bookstores that they can go to, and and Goodreads and whatnot. I have a website, KristyHamilton.com. And I'm also pretty avid on Instagram if you want to see amazing pictures of nature, but not necessarily science. It's much more nature focused on my Instagram, much more just social, me out in nature, appreciating it. If you want to see more of my work, you can go to my website.
All right, awesome. Well, that's it for this show. I hope you learned as much as I did. Be sure to take a look around your house and notice if some of your things are modeled after objects found in nature. Before we sign off, a quick reminder to like this episode and leave a comment on anything you found interesting. Until next time, I'm R Olson.